a sudden technical thing that we need to, I had to address. So I did see that something was happening, didn't hear anything, but we should get things going. Someone is calling. Yeah, go ahead.
Somebody's kicking us out from the meeting. Just if you can manage who can kick out people so that this doesn't happen.
Okay, let's see.
Last time somebody kicked me 5 times.
Every time he does the same thing. I think
it's one person.
He's 5 years old or something.
Okay, that is not good. Let's see if something can be done about that. So go ahead.
When host left, Zoom pick a random guy, a host. That's why it's hard to identify who is expelling or removing participants.
No, everyone can remove everyone. It's just that if you, sir, can manage the permissions, who can remove people, then please do it.
Let's see. Just a second. All right. Of course, it's not loading. It never wants to load when something like this happens. Right. In any case, let's do it like this. While I try to fix this thing, hopefully it will load in one or another place. We can do the following. I'll share the screen with you in a second. And there's a task that we didn't get to finish last time. But we did discuss this, right? We sorted that out. And what we want is to have the next one. Nope, where you are, this one. Here you go. So there's a diver, leaves a 3-meter high platform, jumps down into water, and we want to determine the force exerted while when she falls into the water. Okay, so you can calculate it in a second, then you'll be able to vote, and I'll try to deal with the permissions.
I think it's okay now, sir.
Okay, so I did change the permissions. It doesn't specifically allow one thing or the other. But hopefully that will fix it. So if you have problems, do tell me, and we'll see what we can do even more. Yeah, all right. So which one is it? You can, in addition, of course, vote on it. It does work. All right. There you go. You can vote which one is the right one. So diver jumps down the platform, goes into water, and stops in 0.1 seconds. All right. So 90%, 1500, then 6% for 2300, and what is it? 2% for 3100, 0 for 12, and 38. So what can we do and what should we do in this specific case? So we have a diver jumping from 3 meters above the water, goes in, and inside the water we go from, well, close here we have velocity 1, and then at some point we have velocity, let's say 2. After 1.2, oh sorry, 0.1 seconds. So we want to find force. We want to find force exerted on this diver. Right. So, and maybe the last thing, that there's initial velocity. Starts from here, falls down, gains velocity, and then loses its velocity. So we know that dp dt, and dt is the force that will be generated here. Of course, it means that we have 2 minus v1 divided by delta t, and in this case specifically our delta t is 0.1 seconds. Mass is 50 kilograms. What is the velocity? So we assume, and as you can see, so the enters the water and stops, means that the final velocity at the very end, v2, should be 0. And then, well, we have some sort of velocity there. What is this velocity? So this velocity right before we entered the water is, well, a velocity that the diver has reached. Let's assume that the initial velocity is 0, 0 meters per second. 0 meters per second. And so it starts. Are there any accelerations in this direction? No, that what should happen on Earth. So there is free fall acceleration. If there is free fall acceleration, then the v1 should be v naught plus GT. And from here, we know we can get the velocity to put in here if we know the time. How do we get the time? In this case, we know that the height, or maybe let's do it, the height can be described, so the length that a object with constant acceleration will go is equals to v naught t plus at2 divided by 2. This part is equals to 0, so this is 0. And there we actually have, well, gt squared divided by 2. On the left hand, so the height is 3 meters. It will fall down for 3 meters. We'll cover specific time, get to this velocity, which means that we need to take both of these and combine them. So we can determine time from this one, which is what, 2h divided by g square root, and in the other one we have 1 gt, and from here we get that velocity 1 should be g times 2h divided by g and square root. To make life much easier, and we don't have to use calculator for this case, let's take g as 10, but again, so that we don't have to overexert our fingers. 2, 3, 10 square root, which is 6 divided by 10, 0.6, which is square root of 0.6. 0.6 and here and that. It is 0.77, so here we have 7.75 meters per second. Right, so we have the velocity. Now we can plug it into here and get 50 times, well, 7.75 divided by 0.1. Negative and 50.01, which should be 3872. Newtons. Negative. What did we have for the answers? 3840. 72. I must have rounded something up. Well, I did take 10 and not 9.8. Let's see if 9.8 gives a better result. 9.8 square root of 69821. 7.6 and 50 and 0.1 and all right. So if we would take the correct value, not 10 but 9.8, we get to the result of that is, we get to 3.8 and 3.6. So as you can see, roundup is the reason for the change in numbers, but in one or the other direction, it is not very important. It should be 3,800, and well, it is. Now, regarding the questions that you have, the first, can we take 3 meters and second? That's the important thing here, that in this case here, we have that the diver stops in water in 0.1 second. Not that it travels the time. It doesn't fall for 0.1 second. It travels for some time that we found, and it stops. So the change in momentum happens for 0.1. I mean, squared mgh. So in this case, we could use kinetic energy, of course, but technically, from perspective of lectures and things that we have covered, we haven't defined energy technically. So that's why we're not using the energy. But of course, energy can be used. It is very useful when we have defined it. But again, for now, we technically have not. So 1, and then we get here, we would use that. Then we get to this result, which is a little bit better. All right. So as you can see, the important thing is to look for where. So where does the change momentum happen, and what is the time period for that change? Right. Next thing that we have to go over is, well, basically define the reason why we can travel. To find the reason why we can travel is following. To go forward somewhere, we need to feel some amount of force in specific. Okay, so if we want to go forward, it doesn't really matter which direction is forward, but if we want to go in one direction, we need to have force. If we're going to have force, we're going to have acceleration, that we know. And now the question is, what is the thing that helps us produce this force that we are going to go in that direction? Well, if someone throws us from a top of the building or something, then obviously there's a specific force working on us, which is sort of intuitively clear. But in some situations, the reason and the source of this force is not exactly clear. So we have to look specifically at, in any setup, we have to look for the direction of the force and, well, the source of that force. Which brings us to the Newton's third law, which I'm pretty sure you know. But technically, it is if one object is interacting with another object, they are, well, interacting. It means that one object is applying force to the other one in a specific direction at a specific magnitude. Then the other object will apply the same amount of force to the first object. First and other, or other and first. That is not very important. So that these forces that they will interact at will be equal, just with the opposite sign, which is, of course, third Newton's law, or Newton's third law, which is that on any action there is a reaction. If I push a wall with certain force, then the wall is pushing towards me with the same amount of force, just in the opposite direction. Again, in everyday life, we know this very well. You have used it in everyday setting or in school. What is not obvious right away is that actually, because of Newton's, or rather Newton's third law, tells us that we can travel in space. We can walk, we can drive, we can fly. All of these things. All of these things are possible because we have, well, that's the explanation. All of that can be explained with Newton's third law. And you can ask a question. So, how exactly? Where do I see that? For example, in walking, I'm I'm just walking. I put my foot on the ground, press on it, and I walk forward. So the thing is that if that is the case, or when that is the case, rather, I do press my foot on the ground. It means that I'm pushing on the ground with a specific force, and I am creating acceleration for the Earth. But at the same time, the Earth is applying the same amount of force towards me. And if there's that amount of force, then, well, there should also be acceleration. And the tricky thing here is the following, or rather something that actually tells us how this exactly happens, is if we know that there are two forces in the working in the opposite direction, and we apply second Newton's law and look for the acceleration created with proportionality, well, or proportionally to the mass of the object, we can see that the more massive object is, the lower acceleration will be created if the second object is much smaller. And if we think about it, I, as a, well, comparatively to the planet, tiny speck of mass, will never be able to create in any imaginable way enough acceleration so that the Earth really changes its course in space. But because the Earth is so massive and I am comparatively so small, all the acceleration that is created is basically going into my acceleration into me. So the Earth is creating huge acceleration comparatively on me, which is, well, proportional to whatever I'm trying to push or create with my force pushing the Earth away. And very similarly, as if we have some stationary object that is, well, firmly connected to, let's say, same Earth, any building or anything like that, we don't see it moving. We don't see it having acceleration or changing its movement whatsoever. But technically, we are creating some amount of acceleration, which is just negligible. At the same time, because this system is so big, we can feel the acceleration that this object is creating on us because of Newton's third law. So any kind of propellant is also based on this. Any kind of traveling is also based on Newton's third law. Yeah. In case of change of momentum, this Newton's third law is not as important as the one that we just looked at, the diver. Okay. Now, where can we, or how can we get to some other forces that are important that we should talk about? So when we talk about gravity and Newtonian forces, we are talking about Newtonian gravitational explanation, which is good as long as we want to explain simple things, or rather objects being far away, or very big objects that, well, we interact with. In this model, we know that roughly gravity is working around the Earth at all times in just the central direction towards the core of the planet. And we can ask why specifically. But the general idea is that any two objects in the universe are attracted with this gravitational force. We can describe it as follows. So it is dependent on how massive the object is, and it is inversely dependent on how far away they are, these two objects. And there is some proportionality coefficient, which is the gravitational constant. Now, again, in this model, any bit of mass is interacting with this force with any other bit of mass in the whole universe. So I am pulling Moon right now with some amount of force, and the moon is pulling me, obviously, with some amount of force. So we're constantly in superposition of the forces all around us, and that is why we can, well, exist like we do. Now, the problem, or rather sort of a problem, is that most of the objects are so far away, and or they are close but they are very small, that we don't feel this interaction. What we do feel, which is much more visible, is the interaction with something very, very massive that is nearby, which is the Earth. So there we say, okay, if that is the interaction between a object, any two objects with mass, we can say, if we look at the surface of the Earth, we can calculate this gravitational force on surface of the Earth at any given point. Then we can say, okay, on one hand we have this. At the same time, we have the Newton's second law, which means that any force will have to create acceleration. And if we apply that, so put on the left side that the acceleration times mass is on the left-hand side, and on the right-hand side we have the gravitational force, we see that our mass will cancel out, and we are left with some acceleration that we actually are calling the free fall acceleration. So we get it from the Newtonian gravitational force and second Newton's law. We combine those on the condition that the Earth is perfectly round and the distance between the core and wherever we are on the surface doesn't change. On the condition that the Earth is homogeneous sphere, a perfect sphere, and the most of the mass is in the core. So in that case, we can calculate that, well, our free fall acceleration should be something like 9.81. Of course, in reality, that is not really the case. There are inhomogeneities of mass. The mass distribution in the planet is not homogeneous. The size, or rather the distance from the core at any given point, is also changing. Himalayas, for example, or Mariana Trench, although that's not really surface of the Earth, but still quite a bit of difference in height, and thus the actual free fall acceleration can change, or rather does change, depending on where we are on the planet. But as a general rule, we say that, well, it is 9.81 as an average value for the whole thing. So if we do change the height, we can have decrease in the free fall acceleration. That's why at some point, far enough, we can just let the satellite go, and it keeps going on, because we don't have this free fall acceleration or gravitational interaction between the Earth, the planet, and the satellite. That's how we can, well, travel or make things travel far away. And from there, if we do think, or rather talk only about the surface of the Earth, we can use the thing that we're using in everyday life quite a bit, which is actually what we're using and not what it represents. We can use weight. So we can use weight, and the weight is with the acceleration that Earth is creating due to gravity onto us, and it is pulling us down. We're falling constantly. Times the mass will be the weight that we are using in everyday life. So the weight actually is how much force we are creating on the surface that we are standing on. So that is the weight. And if we look at it schematically, so this is us, we are pushing onto the surface. From the Newton's third law, there is a force in the opposite direction, which we call the normal force. And we can look at a couple of situations, for example, if we're just standing still, nothing is happening. So we're really, let's say we're weighing ourselves. And then we are trying to, well, we're pushing, and we can just calibrate it into some number proportional to something else, to some number that will calculate for us the mass we have. And that's why we use kilograms and etc. when we talk about weight. Exactly. You think that mass is weight. Now, what we have then obviously is, well, our weight is equal to the normal force as we have it. Now, if we start to move around with our system, let's say we take scales, we put it in an elevator, and then in an elevator, we can go either up or down. So we're going to have acceleration of the whole system at the same time with the acceleration from outside from the free fall acceleration. And what we're going to have is, well, we're going to have a superposition of both of these. Now, even there we have two situations. So technically we get something like this, and rather something like this. So we can see that the weight is, well, a superposition of both of these, but the direction of our acceleration is important. So if we're going in the opposite direction of free fall acceleration, so accelerating upwards, then our weight will increase. And if our weight increases, we can say, while I'm in an elevator, can I really become heavier? Well, weight increases, but that is only because it is the measure how much force do we apply onto a surface. Now, if we go the other direction and we start to fall down, we see that we can get to a very specific point. So we get lighter. That's one thing. And then we can have a very specific point where we have no weight whatsoever. So if the system is falling down with free fall acceleration and we are within that system in our scale with our scales, and we're falling with free fall acceleration, then obviously we cannot exert any force onto that surface because, well, everything is falling down at the same rate. So we can have weightless state. We cannot have massless state, or not so far, not really, not in an inertial mass context, but we can have weightless state. There we go. All right. Okay, let's do it like this then. For example, we have here two things. Let's get that away. Sorry. There we go. So we have some object that is that weighs 20 newtons. It is 20 newtons. We know that weight 1, let's say, is 20 newtons. And at this, we have free fall acceleration, which will call G1, 9.8 meters per second squared. Now, what we want to know is what is the mass and what is the weight at a different point where the free fall acceleration is 4.9. What do we have? So at the second place, we're going to have mg2. Okay. So how about this mass? We know what? We know that the mass does not really change. It means that the mass should be the same as in the first situation. So 1 mg1. Which means that actually we can just delete that. The mass should be equal in both cases. We can find mass here. P1, G1, that's an ugly P. And then we can plug it in here. So our P2 should be P1 G1 times G2, which is, what is it? 20, 4 point, oh, sorry, that's 9.8. And here we have 4.9. All right. That's what we get. So very roughly, we're going to have, we have the free fall acceleration in the second place twice as low as in the first place. So the the weight will also be twice as much. So 24.9 and 9.8. Sorry, the weight will be 2 times lower than it was there, and I get is 10.1. I actually get 10 newtons. All right, so a simple thing, but we should just remember that that is the case. That is the case. Okay, a couple of things. Last two forces that we want to look at is elasticity force, which again, empirically we know quite well. If you have something elastic, you can extend it and contract it and then let go. It will get back into the same form and length as it was. A spring is a very good example. So if we have a specific material that we extend and we look at the distance that we have extended it, so we have applied certain amount of force to extend it, and at the same time, the more we extend it, the more force we need to apply for it to be extended, and it means that there's a elasticity force working in the opposite direction. So we apply force, we feel again that there is an opposite direction of the force within the material, and that is proportional to how far we extend it and some intrinsic property of material, which is elasticity coefficient. And this is called the Hooke's law. Obviously, the minus sign here is because, well, we apply external force to, let's say, extend it or contract it, and the force, the elasticity force, will be in the opposite direction. And X here is the deformation, as I mentioned, elasticity coefficient. And again, that is something that we know quite well. If we look at a classical example, which is a spring with some mass, it will do its thing, right? We can measure how much force we have to apply with the set amount of mass for the set amount of extension, and we get this linear part. Now, if we go over this limit, right? If we go here, release it, it will come back. If we go over, we can have non-elastic deformation. So we will just break the spring. And in this case, spring is just intuitively very simple because we know how it works, but it works for any material. Yeah, any material that you can imagine. The question is how easy it is to do that. Here with the various weights, it just, if it's in the gravitational field, it will just more weight will be more force that we can apply. All right, so Hooke's law, elasticity. So if we try to remember or write things down, so then this is something that we do want to write down. Now, and the last thing is force of friction, something that we have talked a little bit about. Again, if there is there are two kinds of frictions we should think about, static and dynamic friction. In this case, we can have dynamic as a sliding friction. Friction is dependent on some coefficient and how heavy the object is. Because we have the normal force working from the ground, and well, we obviously have some weight that we are pushing the ground with. And if we try to move this object, move around, walk, or drag something, we create the friction force in the opposite direction. And as I mentioned, the friction force is proportional to the coefficient of friction, proportionality coefficient, and the weight of this object. Now, the really important thing is that the friction force is in the opposite direction of movement. So that is why we can walk around. We are pushing on the earth. We are creating friction, and one force is working one direction, and then there is the opposite force, and the one that we feel that lets us go forward. And friction force is dependent on velocity. The higher the velocity, the higher the friction force. Not in all cases, but in some cases, the higher the velocity, the higher the friction force will be created. And another thing that we empirically again know, if we have ever tried to try to move anything around, where we also see that there is a limit to certain limit to the friction that we create. Or if you have jumped out of a plane and reached a terminal velocity, which is just we start to fall at a constant speed because, well, we fall quicker, the friction force is higher, we fall quicker, the friction force is even higher. And then at some point, the drag, the friction force created by the air is it cancels out certain amount of our velocity, and we are just falling at a set velocity. We're not accelerating anymore. If that wouldn't be the case, then we would reach extreme velocities when we reach the ground. And here with the sliding force, we also have the same thing. If we don't let the object to stop, we have lower friction coefficient for sliding force than for sliding than for static. And this is how we can describe it. If we have a fridge to move, the most complicated, the most amount of force we need to apply is to start the fridge going. Right? We start it, then it's not as bad. And with that, we gonna answer the last question, or rather, I will leave you with the last question here. So we have anti-brake system. We want to, in the car, if we go and there is something slippery, we want the tires to keep rolling on. ABS and car. And the question is why? Why do we want to do that? So let's do like this. You can vote. And when you are done voting, we can take a break. 23 minutes. Fine, let's round it up. So past, let's come back and, well, carry on. So as soon as you are done, take a break and see you at past. All right, I think we can carry on. You say it's B. How do you know? Well, it is B. In that specific case, we want to have as high friction coefficient as possible, because the more friction we have, the more maneuverable the car is. And we can assume it is not exactly that, but we can assume at the sliding situation, the really sliding situation when there is, let's say, ice, a little bit of water, and car goes over, the friction coefficient goes almost to zero, or we can say that it is zero, and thus you can't really do much. That's why, well, things like that are being invented so that we can do something about it. All right, now the next thing that we want to look at very quickly is a system of particles. And for the system of particles, we need to separate into two things, external and internal forces. And we will be looking at closed systems. In mechanical perspective, or from mechanicals, closed system and open system is not as complicated, or the influence is not as complicated as it would be, for example, for thermodynamics. Then we're going to have assumption for closed systems, but actually in real life we have more open systems, and that's one thing. But here, closed systems, that we are talking about something, there are, let's say, no losses. Well, when we'll be talking about losses, there are no additional things coming in or out of this system. And in case of system of particles, is set number of particles, the mass is constant, it does not change. And then we can talk where specifically these points are, what is the combination of, so what is the geometry of this system? That's the question we can ask. And why can we ask that? Because eventually we'll see that the geometry of an object and the mass distribution is very important. But so far, we didn't care for the geometry. We were talking about single point or mass point mass object, and that was fine for us, right? For kinematics and dynamics, that is totally fine. We have some amount of force working on an object, there is acceleration, the mass point is moving, etc. But in reality, everything is not as simple. Well, the objects are big enough. We have specific geometries for objects, and there we have to, or we can rather, do two things. Either treat each point in the system individually and look at the full description for each point, or we can assume, well, and which works perfectly fine, we can assume that the whole mass is focused in one point, in center of mass, and if we move or apply force to that point, we can move the whole object. In many cases, that is the case. If we find the center of mass and we apply force there, then everything else moves with that, and we just make our life much, much easier. And there, again, if you have ever been on a boat, I mean, small enough boat, not a big one, you know what is the most stable position to be in the boat with very low center of mass within the system, or if you have tried to wrestle with someone else, you want to, let's say, throw someone off of its feet, then again you have to look for the lowest, or you have to lower your center of mass and center of gravity to have the necessary leverage for the person. Why that specifically is why you have to lower it, we'll talk a little bit later, but intuitively you know what to do. Intuitively you also know that if you are slipping, you are doing something very specific with your body. You're trying to lower the center of mass and spread out and have as high surface as you can have, so that we increase the friction to a certain extent. Well, and increase the moment of inertia, but that's something else, right? Okay, so how do we find it, and what can we do? Where exactly that is? Again, empirically, you know how to find it. You know how to use it. That is true. Shorter, wider objects will have lower center of mass. Oh, because they are shorter. Because they are shorter. Now, so if we have two objects, let's say identical objects, and they are in different positions, what we want to look for is the center of mass, which is exactly how it sounds, right? We are looking for the single point within that system that will have the best distribution of masses comparatively to the whole system. So in this case, in this specific case, we have one object here with one mass, and we have another object with another mass. And as you can see, they are quite a bit different in different places. So for these two objects, if they're the same in, let's say, a how would you? Yeah, okay. So if you are, let's say, standing on one foot and you have some weights in your hand, right? If you extend apart from some additional things that will come in mind, but if you extend your arms fully, right, you know where the center of mass technically will be. Assuming just that the weights are in there, then obviously they will be somewhere in the middle. Now, if you will push one closer, right, so the distance between, let's say, your core and the weight to one side will be different, then the center of mass actually will change. And if that is the case, then let's say, and you are trying to stay on one foot, then obviously you will be pulled towards one direction, again, because of the free fall acceleration, because of the gravity that we have. And something like that is, well, again, intuitively should be clear. The way how we find it is, as you can see in the formula. Regarding this, and well, in case of tests, for example, you should have a general feeling of why this works and how it works. How can you find these things? It won't be necessary to find numerical values for center of mass. But again, this is something that you have used in your life a couple of times already. All right, and let's say we have a more complicated system, a object with some geometry, and then we look at, again, what we would do to find the center of mass. We would look for each of the points of the object, look for how far they are from the center of, with respect to the coordinate system, and we'll look for this middle point in there. There is one work which is physical pendulum, which is a piece of iron that you stick on a wall and then look how it oscillates. And to find the center of mass there, you would take different points, put it on the wall. So put it on one point, balance it, and then look for what is the straightforward direction downwards, and try to find where these downward lines intercept, which So the question is, since the center of gravity is near abs area, will stronger abs make you harder to push? There you have to look at the direction of pushing. We'll be done with the pendulum first, and then we'll address this question. So with the pendulum, the idea is like this. So the pendulum is something random. Let's make it a little bit less random. So this is how you do it. There are some holes, and what you have to do, you have to put it on in these holes and oscillate it, and then look how does the period, for example, change for these oscillations, but we're going to get to that too. So how do you find the center of mass of this kind of object? What you do is you take one. Oh no, I need all of it. You take one hole in this case, and but I want to move it around. It doesn't want to move. Oh, there we go. So, all right. So let's imagine that there are holes. So we would put it in one hole and make it oscillate. Let's say, so just put it downwards. Let's say here. We would look for a line that goes straight to the center of the Earth from that point that we have found or used there. Now, then we would take it and rotate it a little bit and look for the similar line, just from a different hole. Then rotate it again, look where the line goes directly downwards. Again. We do it a couple of times until we find all the lines, and let's say we have found all the lines like so. The last one is very bad, and there we go. And there is going to be a point where all of these lines intersect. That's going to be the center of mass for that object. And when we put it like that in there, if there is a hole, it will be in equilibrium, relatively in one direction, because the separation of mass will be roughly equal. Okay, so regarding the abs, so let's assume there is a person. We have a person with very strong abs, a six-pack. Let's assume that the center of gravity is also roughly there, and now the question is, if you have a six-pack, is it better than not having a six-pack? There you go. Obviously, the answer is always having one rather than not having one. Should have copied it without first. There we go. All right, it's somewhere there. Okay, so the difference is, well, your strength in the center of mass will be in the same position, roughly. The distribution, if if we just talk the influence of having or not having strong abs. So the center of mass is the same. The distribution of mass doesn't change, right? Because, well, it will change a little bit because you should have more fibers in there comparatively, so more mass than not having it. But if we assume that it is in the same place, the center of mass is in the same place, then applying force in this direction will not really influence the momentum that you can create onto the person. What will change, though, is the ability to withstand one direction or the distribution of force. So in this case, if there's soft tissue there, then it will be a point impact. Pushing or hitting, it is not that important, but it will be a smaller area. Well, let's say a area of a palm, right? And if you're pushing there, then, well, everything that goes, all the force that goes in will go into that area, and let's say you can have tissue damage. If you have a stronger abs, then you will have a better distribution of force that goes onto the body, and it will be able to withstand more force, but from a perspective of generating torque and or generating inertia in both cases. In both cases will be the same. Yeah, it should be the same. All right, a little sidestep, but okay. Now we have defined this, and the last thing which is important is that if we do have we know where the center of mass is and center of gravity, then obviously applying force or moving the system, we can assume that everything is again located in the center. We don't have to talk about each specific points and the, let's say, amount of movement, but we can just say that all of the mass is moving as the center of mass is moving. One important thing that we should consider and remember is that the center of mass is not obligatory. Not obligatory inside the body. So right here, I've given a couple of examples where it was, but there are objects that do not have it inside the body. If we have a toroid, like a donut, then the center of mass will be in the center because, well, a distribution of mass is roughly around a set point. But because it has a middle hole in the middle, obviously center of mass is there also. And then there are, well, boomerangs which do fly in specific way because there is a displaced center of mass comparatively to everything else. And I was pretty sure I have an image of another place where we can have it, but okay, well, I guess it is how it is. It is how it is. Okay, so another thing that, or rather the next thing that we should remember, consider, and use, we will have to use actually, this is something that we will be using at least 1 or 2 times, is what happens if we have a system of particles, or what happens if we have 2 objects and they are colliding. So we were talking about collisions and cars and change in momentum, linear momentum. Okay, but what happens if we have 2 cars colliding with exactly is happening with that momentum in one or the other case? We know there will be force, or should be force, but we should also know what direction. Now, and here we need to figure out one thing first. So if we have a system of particles and they are interacting with each other, we can separate the interaction in two sets. So internal forces and external forces. So let's say we have a collision. We have the amount of momentum that goes into one object, the amount of momentum goes into the other object, or rather the momentum it has. They interact. From the third Newton's law, we know that, well, if I push onto something, that something will push back on me. Okay. So there is this change in momentum and interaction from outside the momentum. And then there's the interaction within. Well, when two surfaces are interacting with each other. So if we separate into these two things, again, internal forces and external forces, we could look for the overall change in momentum, considering both of these. Okay, in this specific setup, but actually in general too, what do we have? We have momentum of change of momentum in the first one, change of momentum in the second one, and now here we do remember that there is Newton's third law. So the internal forces will be in the opposite direction. But if they are in the opposite direction, it means that if we look for the momentum of the system of particles, then there is a difference. There's a difference between internal and external forces, and we have the cancellation or compensation of the internal forces, and we're left only with the external forces. So that the general momentum, overall momentum, change of momentum will generate force, or to change momentum we need force, but we need external force. And of course, because we know center of mass, we can also say that about the center of mass. But again, the very important thing is that we cannot change momentum from within the system. Only external forces can change the momentum of this system. Yeah. So this is the most important thing in this specific case. Do you want to now ask a question? Okay. All right. And just to reiterate, again, center of mass is behaving as if the total force is extended on the center of mass, on the whole, all particles. All right. Now, why the change in momentum with external forces is important? Because when we look at the conservation laws, and we have the conservation of linear momentum, we can look at a system and see that indeed there is no way how to change our momentum from within. And you can test it rather easily. Try jumping into a pool or water, or actually jumping in general, and then in midair, change your momentum. If you are falling, try changing your momentum. That is impossible. And because we need external forces. If you say, but I can jump and twist, well, you have to really think, how did you get to twist when you are jumping? Most likely, you had not just, say, jump up and turn around, but you were not jumping up, you were jumping with a twist already, and etc. Okay, now, conservation momentum. So if we know that if there is no force applied, then we know that there will be no change of momentum, which means that the momentum will be constant. And if that is the case, then we can look for three directions. Well, we have three components and change of momentum in each component. And in this case, just for the x direction, but the idea is the same in all 3 dimensions, which means that if we have a set amount of momentum at some point, at some different point in time, we should have same amount of momentum. But if something has happened, let's say a collision, or we lost something, or we threw something out, then we just have to consider all of the parts that are now separated. And there is no better obvious example as a shooting cannonballs. In addition to a couple of additional, in addition to, let's say, jumping from boat to boat, or ice skating, where you try to do something while you are skating, and things like that. So let's look for a specific example here, because we can have slow motion interaction in here. Okay. So what we are looking for is, well, in general, people are, or were not, I don't think that they are doing that now. People were meeting other people in the middle of a field, shooting cannons because, well, shooting cannons, and because people like things like that. So here we see many things happening right away. As you can see, the cannon went back, right? It shot the cannonball, and it came back. So here we already see the conservation of momentum, that if something is moving in one direction, something else, or in this case stationary, will also have the momentum going backwards. In addition to that, we see that the Newton's third law is working perfectly, right? There's force in one direction, there's also force in the direction. In addition, there's some parts of molecular physics, expanding gases, blowing up, and things like that, but that is not what we're interested. We are mostly interested in mechanics of this thing. And we also see very well first and second Newton's law, and the importance of frame of references. He's talking about additional things that, well, they were calculating how quickly the sound wave and pressure wave is traveling, but that is not important for us for now. Okay, and then, well, again, some more shooting. We again see that, well, it shoots out a cannonball and comes back, rolls back because, again, conservation of momentum here in slower motion. No. There we go. And the really important, another important thing, how can we tell that there are working various laws of Newton's, various Newton's laws, is if you look for how the momentum is actually transferred from one object to another. So there should be there we go, quite a lot of momentum traveling, things flying off, and hey, I don't seem to be able to find, wait a second. Too far. There we go. As you can see there, could see here. Changed the wrong one. What we're interested in is the transfer of momentum from the cannon itself. It goes back, as you can see, and there's a little lag, and then everything else goes back, right? So there's transfer of momentum from the cannonball, so from the cannon and cannonball, then it goes to the next thing that is connected to that system, which is, well, the body of it. Then that body is connected to the wheels, and then everything in this chain reaction slowly, well, not really slowly, but step by step is transferring the momentum from one object into the next one. Let's see here. I think we should be able to see it again. So look for the cannon itself. It goes back, then the whole body goes back, and then the wheels and everything else. All right. Now, when we see that and we think about how can we describe it, we see how, oh, we're almost out of time. Shucks. When we see how that is happening, then the next thing that we want is not just the, well, cannonball going one direction, the cannon going the other direction. We also want to look at collisions. So what happens if we have two objects colliding one into another? And for collisions, the worst case scenario is something like this, where something bad happens. But good case scenario, something that we can enjoy quite a bit, is, let's say, pool. In pool, collisions are happening. Exchanges of momentum is happening at any given collision. And you can calculate all of these and apply various things with having fun playing pool at the same experiencing physics doing that. So where we're going to stop is we have to look at two general differences between collisions, and then two additional differences between collisions. As Akash has mentioned, there are elastic and non-elastic collisions. So elastic collisions where we have just pure exchange of momentum, we're going to look at that. And non-elastic collisions where we have some deformation, when the momentum is not really conserved. But we will cover that next time. And for the second general separation of various collisions is there are direct collisions. So let's say we have here two objects colliding, but they are colliding at a specific angle one to another. There's a collision line, and if the velocities are off this collision line, that is not direct collision. If they are, we can have a direct collision. And of course, if the collision is direct, it is much simpler, right? Exchange of momentum. Some of it will look how things have changed. And if it is sliding collision, then, well, we have different velocities. And so we have 2 minutes, right? We'll stop here with this, and I'll just share my experience with collisions, and first-hand experience, I guess, with collisions when I was in grade 3 or something like that, maybe 4, maybe no, it doesn't matter. When I was small enough, we were running around. Of course, I was running into a classroom. My classmate was running out of the classroom, and we had a direct central collision because there were no angles. We were really on the colliding line, on the collision line. We bumped into each other, and I think he was smaller than me, or he had lower velocity than me, and he fell on his back. I stopped there in the doorway. So from a very young age, you might also have experienced these kind of interactions and conservation of momentum in that kind of setup. All right. That's going to be it for today. I'm sorry that we started a bit late comparatively. No, I did not fall. He did, and hit his head, and had to go to a nurse to put some patches on his head, which is maybe not very nice, but well, it is how it is. I had higher linear momentum than he did, and I don't know. I might have also lower center of mass at that point, and that might be additional reason why I didn't fall down, and he did. But I mean, it was when I was very young, so the memories are a bit murky there. In any case, thank you very much for being today here, and if you have any questions,
Sir, I couldn't
Go
find for the class.
what did you find?
I couldn't find the link for the class.
It is in Artis. You know what? I'll make it red or purple or some color so that it jumps out. That might be the reason.
Okay. Thank you.
Mm-hmm. And here. That's true. Yeah. In that meaning, short people have quite a lot of advantage falling down closer to the earth and whatnot. All right. And so as I mentioned, that's going to be it. And have a safe end of the week, and see you next week. Bye-bye.
Bye, sir.
Thank you. Bye.
और वाले में